Assalamualaikum and hi everyone. We meet again in lecture 5 of chapter 1 integration. Now we're going to look the use of integration to find the volume of a solid of a revolution. Volume of solid generated by revolving the region by the curve and the x-axis and y-axis. In this section, we use integration to calculate the volume of solid. Consider the solid of revolution in the following figures, which are formed by revolving certain region about an axis. So for the first one, we have a constant function. So when we revolve the constant function about the x-axis, it will form a solid of a cylinder. Another example, if we have a linear function, and when we revolve about the y-axis, and it will become a solid cone. So by using an integration, we can find the volume of the solid. Okay, now we want to find the volume of a solid of revolution when revolve about the x-axis. The volume of the solid generated by revolving the region about the x-axis between the graph of a continuous function y equals to fx and the x-axis from x equals to a to x equals to b. Okay, now we look at the graph. Let's say we have a function y equals to fx from x equals to a and x equals to b. So this is the region. So we want to find the volume when the region is revolved about the x-axis. So the formula for the volume is v equals to integration from a to b pi y squared respect to the x. Since y equals to fx, so the formula of the volume is integration from a to b pi fx power of 2 dx, where fx is the function in terms of x. Since pi is a constant, so we can put pi in front and we just integrate from a to b for the function fx squared dx. Now we look at the volume of a solid of revolution when it revolves about the y-axis. The volume of the solid generated by revolving the region about the y-axis between the graph of a continuous function x equals to g of y and the y-axis from y equals to c to y equals to d is illustrated in the figure below. So from the figure, we can see that the blue line represents the curve of x equals to g of y, and it's bounded by the line y equals to c and y equals to d. So this is the bounded region and is rotated about the y-axis. So the volume is v equals to integration from c to d of pi x squared respect to dy, and since x is a g of y, so by substitute the x, the formula of volume is integration from c to d pi times g of y squared respect to dy, and since pi is a constant, so we put pi to the front and we can simply integrate from c to d of the function g of y squared respect to dy. Example 19. Find the volume of the solid form when the area bounded by the curve y equals to 1 over x, y-axis, y equals to 2, and y equals to 5 is rotated about the y-axis. So from the graph, we can see that the curve y equals to 1 over x from y equals to 2 to y equals to 5 is rotated about the y-axis. So if you want to find the volume rotated about the y-axis, so we have to find the function x in terms of y. So I have as x equals to 1 over y. So the volume for the bounded region is v equals to pi integration from 2 to 5, and the function is 1 over y squared dy. So we just expand the square, so I have 1 over y squared dy. So when we integrate 1 over y squared, so we have here as negative 1 over y from 2 to 5. So by substituting 5, so we have as negative 1 over 5 minus, and when we substitute 2, we have negative 1 over 2. And as we simplify, so we have 3 over 10 pi unit cube. Now for example 20, let R be the region bounded by the curve y equals to negative x squared plus 1. So calculate the volume of the solid form when it is rotated about the x-axis. So I highly recommend that you do a roughly sketch so that we can have a picture about overall function that might be involved. So this is the function y equals to negative x squared plus 1, and we can see the bounded region R. So the volume when the region bounded rotated about the x-axis is integration from negative 1 to 1 of pi, and the function is negative x squared plus 1 squared respect to dx. So we can expand the function as x power of 4 minus 2x squared plus 1 respect to dx. So we have pi, and we integrate the function x power of 5 over 5 minus 2x cubed over 3 plus x from negative 1 to 1. So I continue over here. So as we substitute the integral about x equals to 1, so we have 8 over 15 minus, and we substitute x equals to negative 1, so you have negative 8 over 15 So we calculate, and the final answer is 16/15 pi. Next, let's see the volume of solid generated by revolving the region between the two curves. First, let's see the volume when it revolves about the x-axis. Suppose that y1 as fx and y2 as gx are non-negative continuous function such that fx is greater than or equal gx for a less than or equal x less than or equal b, and let R be the region enclosed between the graph of this function and the line x equals to a and x equals to b. When this region is revolved about the x-axis, it generates a solid, as we can see illustrated in the figure. So the upper function is fx and the lower function is gx. So this is the bounded region between the two curves in the line x equals to a and x equals to b, and the region is revolved about the x-axis. So the volume of the solid generated by revolving R about the x-axis is V equals to integration from a to b pi times upper function y1 squared minus with the lower function y2 squared respect to the x, or we can simplify as the volume is integration from a to b of pi times fx squared minus gx squared respect to the x. And the second one is the volume between the two curves when it revolves about the y-axis. Suppose that x1 equals to fy and x2 equals to g in terms of y are non-negative continuous function such that fy is greater than gy for c less than y less than d, and let R be the region enclosed between the graph of this function and the line y equals to c and y equals to d. So when this region is revolved about the y-axis, it generates a solid, as we can see in the figure beside. So we have here as fy and gy from y equal to c to y equals to d, and it revolves about the y-axis. So the formula of the volume is integration from c to d of pi of the function x1 squared minus function x2 squared respect to dy, or we can use the formula of volume is integration from c to d of pi times fy squared minus gy squared respect to dy. Example 21. Find the volume of the solid generated when the area bounded by y equals to sine x and y equals to 1 minus sine x for interval 0 less than or equal x less than or equal pi over 6, and it's rotated 360 degrees about the x-axis. So for this question, I highly recommend it. We can roughly sketch the graph first. So let's say we have the x-axis and the y-axis. So first we sketch the graph of y equals to sine x. So this is y equals to sine x. And for the second graph, 1 minus sine x. So this is 1 minus sine x. And for interval 0 to pi over 6. So pi over 6 is actually the intersection between the two graphs, and this is pi over 6. So let's label the graph first. So this is y equals to sine x, and this is y equals to 1 minus sine x. So our bounded region is over here. Okay, now let's do the calculation. So to find the volume of the region that is in between two graphs, so the formula is pi integrations from 0 to pi over 6, and we have to identify the upper function, which is the green line, that is 1 minus sine x, when we have to square, minus the lower function, which is the blue line, that is sine x squared dx. Then we expand the square first, so we have here as 1 minus 2 sine x plus sine squared x minus sine squared x. So I continue on the side. After that, we simplify the function, and we have 1 minus 2 sine x dx. Okay, as we simplify, so this will cancel with this, and then we do the integration. We have x plus 2 cos x from 0 to pi over 6. For a trigonometric function, when we want to substitute the value of x, make sure that you set your calculator into a radian mode. Okay, so when we substitute the x as pi over 6, so we're gonna have 2.256 minus, and when we substitute 0, so we have 2. So finally we have 2.256 minus 2, so we have 0.256 pi, or we can multiply to have 0.8 unit cube. So that's the final answer. So that is the end of the chapter 1, integration.